Have you ever really thought about how your phone charger works? Or how a radio just magically plucks a station out of thin air? Well, the answer, or at least a huge part of it, comes down to this tiny, really unassuming component called the diode. Today, we're going to dive into its one simple but absolutely brilliant trick, forcing electricity down a one-way street. Take a look at this thing. Yeah, it doesn't look like much, does it? It's just a tiny little cylinder, a couple of wires sticking out. But you cannot let its size fool you. This hungle component is, and I'm not exaggerating, one of the true unsung heroes of our modern world. It is the secret ingredient that powers literally everything from your earbuds to the world's biggest supercomputers. It's a tiny giant, and honestly, it's about to change how you look at all electronics. So let me just ask you this. What if you could actually do that? Create a one-way street, but for electricity. A gate that only lets the current flow in, but never back out. That simple idea, that's the whole essence of the diode. And understanding that one concept unlocks so much about how our world works. All right, so let's get into it. How does this electrical one-way street really work? It's time to take a much closer look at the diode and the fundamental role it plays in, well, everything. So the official definition is right there. It conducts current in one direction. Think of it like a check valve in plumbing, or maybe even better, think of it like a bouncer at a super exclusive club. You can go in one way, but there is no coming back out the same door. This incredibly simple property is what makes the diodes so unbelievably useful. Now, if you're going to use diodes, you've got to learn to speak their language. In any circuit diagram, the symbol for a diode is this arrow pointing at a line. It's super simple. The arrow shows the direction the current is allowed to go, and that flat line is the wall stopping it from going backwards. And then, on the actual component itself, that little silver or black stripe isn't just for decoration. It marks that wall side, so you always know exactly which way to plug it in. You know, this little device didn't just appear out of nowhere. The diode story is this amazing journey through time, really, from the earliest days of radio all the way to the absolute cutting edge of technology we have today. It's a great story, full of brilliant minds and these huge discoveries. So it all kicks off way back in 1874. A German physicist, Ferdinand Braun, noticed something weird. Certain crystals only let electricity flow in one direction. He called it unilateral conduction. And that was the spark. Fast forward to the early 1900s, the dawn of radio. The first real diodes were these big, clunky glass vacuum tubes. They worked, but they were not great. Soon after, they were replaced by these tiny crystal detectors in what people called cat's whisker radios. It was a huge deal. But the real, and I mean real breakthrough, came in the 1950s with the invention of the modern PN junction diode. This tiny, super reliable component changed everything and basically kicked off the digital age. And just look at the difference here. I mean, it is night and day. On one side, you have this huge, hot, power-hungry vacuum tube, a real energy hog. And on the other, this tiny, efficient, powerful solid-state diode. That incredible leap in technology is exactly what made our portable, battery-powered world even possible. Okay, so what is the secret sauce? What's the magic inside that makes this one-way street actually work? Well, the answer lies in this fascinating, microscopic place called the PN junction. To get it, we're going to have to shrink down and take a quick journey right into the heart of a semiconductor crystal. All right, stick with me here. This is cool. Imagine a perfectly pure piece of silicon is like a dance floor. Kind of boring, not much happening. But we can spice things up through a process called doping. To create what's called N-type silicon, we dope it with impurities that bring a bunch of extra dancers to the floor. These are free electrons, ready to move. Then, to create P-type silicon, we do the opposite. We add impurities that create empty spots on the dance floor. We call these holes, and they're just waiting for a dancer. So now we've got two materials, one with too many dancers and one with a bunch of empty spots. And that is where the magic really starts. So what happens when we stick the N-type and P-type materials right next to each other? Well, exactly what you'd think. The extra dancers, the electrons, from the N side immediately see all those empty spots, the holes, on the P side and rush over to fill them. But here's the crucial part. Once they pair up, they can't really move anymore. And this creates a thin layer right at the junction with no free dancers and no empty spots. It's a no-dance zone. This is called the depletion region, and it acts like an insulator. That barrier is the diode's one-way gate. Now, if you really want to understand a diode's personality, you have to look at its IV curve. This graph right here, it tells the entire story of how a diode acts. It just shows how much current flows through it at any given voltage. And as you can see, it is not a boring straight line. It's a story with 3 very distinct chapters. Chapter 1 is called forward bias. This is what happens when we apply a positive voltage the right way. It's like giving those dancers a little push, overcoming that barrier, and suddenly, whoosh, current flows easily. Chapter 2, reverse bias. We flip the voltage and try to push the other way, and nothing. The barrier gets even stronger. The gate is closed. The current is blocked. But then there's the final dramatic chapter, breakdown. This is when we apply so much negative voltage, so much pressure, that the gate just shatters, current floods through, and for most normal diodes, that's it. Poof. Game over. So a simple one-way street for electricity. Cool. But it turns out that's just the beginning. The standard diode is really the head of a huge, incredibly talented family of electronic components. By tweaking the design just a little bit, engineers have created a whole lineup of specialized diodes, and each one has its own unique superpower. And you definitely know a few of these family members, for sure. Meet the rock stars, the LED, or light-emitting diode, and the photodiode. They're like 2 sides of the same coin. The LED superpower is turning electricity directly into light. It's what's behind the beautiful colors on your TV and the bright, efficient light bulbs all over your house. The photodiode does the exact opposite. It's the quiet observer. It sees light and turns it back into electricity. It's the eye in your camera and the heart of every solar panel. And believe me, the family just keeps going. You've got Schottky diodes, which are the speed demons built for super fast switching. You have Varicta diodes that are like electronic chameleons, changing their properties based on voltage. You've got laser diodes. Yep, the things inside your Blu-ray player or fiber optic cables. There are even avalanche diodes that are designed to be bodyguards for your other electronics, protecting them from dangerous voltage spikes. The list is huge. Okay, so now it's time to meet the rebel of the diode family, the one that plays by a completely different set of rules. We need to talk about the Zener diode, because it turns everything we just learned completely on its head. Remember how we said that breakdown is bad? That it's the destructive end of the line for most diodes? Well, the Zener diode looks at that breakdown region and says, you know what, that looks like a great place to work. It is specifically designed to operate in that breakdown region, to live on the edge without breaking a sweat. It embraces the very thing that destroys other diodes. Just look at the IV curve for a Zener. It's really beautiful. A normal diode just sort of crumbles and falls off a cliff when it breaks down. It's messy. But the Zener's breakdown is a sharp, clean, perfectly vertical drop. It happens at a very precise, predictable voltage every single time. And that's not destruction. That's control. And that special trick is what makes the Zener so incredibly useful. So what do you do with a component like this? Well, its #1 job is to be a voltage regulator. Imagine you're trying to power something sensitive with a jumpy, unstable voltage source, kind of like trying to fill a shot glass with a fire hose. The Zener diode acts like a perfect pressure relief valve. You can hook it up to that fire hose, and no matter how much the pressure fluctuates, the Zener guarantees that the output voltage stays rock solid and stable. It creates order out of chaos. So when you really step back and look at it all, the diode is this humble, hidden hero. It's working tirelessly behind the scenes in almost everything you touch to make our modern world possible. It really is a tiny giant, and it's an amazing reminder that sometimes the simplest rules can have the biggest impact. I love this quote because it's so true. From the second your alarm goes off in the morning to when you turn off the lights at night, diodes are a constant part of your life. They're in your phone, your computer, your car, even your coffee maker. They are the invisible threads weaving together the entire fabric of our digital lives. At its heart, the diode is just a one-way street for electricity, a dead simple rule. But applying that one simple rule in billions of different ways is what built our entire technological world. And it really makes you wonder, doesn't it? What other simple, fundamental rules of physics are hiding in plain sight right inside the devices we use every single day? Something to think about. Thanks for joining me on this explainer.